We've done polynomial long division before. Today we're going to talk synthetic division. So let me refresh your memory on long division. It's a good idea if you skip any powers, like this one goes from x to the third down to x to the first, to go ahead and put a placeholder in. So I'm going to put a 0x squared in. And then you divide your first term on the inside by your first term on the quantity you're dividing by. So dividing 4x cubed by x gives you 4x squared. Then you multiply that back. If you multiply 4x squared by x plus 1, you get 4x cubed plus 4x squared, and you're going to subtract that quantity from your original. So if you subtract it, you're going to get, careful with your negatives, a negative 4x squared minus 3x minus 2. And then you repeat the process. You use your new first term that you got of negative 4x squared, and you divide that by x. When you divide it by x, you get negative 4x. You'd multiply your negative 4x back by your x plus 1, which gives you negative 4x squared minus 4x. And then you'd subtract that entire quantity. I'm just going to go ahead and flip my signs and make it addition, which gives me x minus 2. Divide x, my new first term, by my original first term. X divided by x gives me 1. Multiply that back. I'm going to end up subtracting and getting a remainder of negative 3. So that goes over what I was dividing by, my x plus 1, because it wouldn't divide evenly into it. And you could either have a minus x 3 over x plus 1 or just a plus negative 3 over x plus 1. So synthetic division is an alternative to long division that you can use when your polynomial is being divided by a binomial of the form 1x plus or minus some constant. So you could do something like x cubed minus 8 divided by x minus 4 with synthetic division, but you couldn't do something like that divided by 2x minus 4 because that coefficient on your variable is a 2, not a 1. So you can only use synthetic division in certain cases. Now that warm-up we did, we could have used synthetic division on, so I'm going to show you how it would have gone using synthetic division. So first you go ahead and put in any placeholders that you need if you skip any powers of your variable, and write down those coefficients. So I'll have 4, 0, negative 3, and negative 2. And now I'm going to figure out what makes the factor that I'm dividing by equal to 0. So negative 1 would make that factor equal to 0. I'm going to take that negative 1 and put it on the outside here, and I'm going to use it in my division process. You just drop down your first number, and then you take and you multiply that number times my value that I have on the outside. So 4 times negative 1 gives me negative 4. I write that down in my next column, and I add those two values together. Then I repeat the process. Negative 4 times negative 1 gives me positive 4. I add that to get 1. I multiply 1 times negative 1 on the outside again, gives me negative 1, and I add those to get negative 3. I need to turn that string of numbers I got into an actual polynomial result. So I took x cubed, and I was dividing it by an x to the first. So that means I'm going to have x squared as my degree of my first term in my result. So that 4 stands for 4x squared. And then decreasing my exponent by 1, I have negative 4x to the first, and then a 1x to the 0, which really x to the 0 is just 1. And then that last term is my remainder that didn't divide unevenly. So it's the same result I got using long division. I can use this synthetic division or long division to rewrite polynomials in different forms. So I can divide them and then rewrite them as my original times what I get divided by plus any remainder that I got. We're going to use this to help us factor higher degree polynomials than just quadratics. So, for example, if you think about just a number, say you take 24 and you divide it by 9. 9 goes into 24 twice. If you subtract 2 times 9, subtract 18, you get 6 left over as your remainder. So you can rewrite 24, your original value, in the equivalent form, 9 times 2 plus your remainder of 6. We're going to do that with some polynomials. So they tell us to write our polynomial in the form x minus k times q of x plus r. So essentially what we're doing is we're using that value of k to tell us what we're dividing by. So we're going to take my original polynomial here, and I'm going to divide it by x minus 11, since we're rewriting it in the form x minus our value of k times our quotient. So if I do my synthetic division, I'll have 11 on the outside here to use in my process, because that's the value that would make x minus 11 equal to 0. It also just is my value of k. So running through here, drop one down, multiply it back, add them, repeat, repeat. You end up with the result x squared plus 11x plus 1 plus a remainder of 12 over what I was dividing by, x minus 11. Which means if I am rewriting my original polynomial, my x cubed minus 120x plus 1, in a different form, I can write it as the x minus 11 binomial that I divided by times my result that I got, my x squared plus 11x plus 1, plus my remainder of 12. So that's equal to my original polynomial. I just wrote it in a different way. I used synthetic division to get there. I could check that my polynomial is equal to my original by multiplying it back together. I'm going to be cheap here and just type this into an app and show you that if you multiply that together, let me scroll down here, you do get our original polynomial, our x cubed minus 120x plus 1. Sticking with that same polynomial, say I want to find f of 11 without using a calculator. Well, that would mean I'd have to plug in 11, I'd have to cube it, I'd have to subtract 120 times 11. It would be quite a bit of work. What I'm actually going to be able to do instead is if I use that rewritten version where I had divided by x minus 11, it's going to be much easier to evaluate f of 11. It's still the same polynomial. I can still plug in 11 and see what result I get, and it should be the same. If I plug 11 in here, however, in that first binomial, 11 minus 11 is going to give me 0. I could plug it into the trinomial and get some stuff, but I don't really care about that because I'll be taking 0 times that. So my final result is just going to be 12 if I plug that in, which is a lot easier than plugging it into my original polynomial. And we have a theorem that basically tells us that. If we took our polynomial and divided it by x minus 11, since we wanted to do f of 11, the remainder we get in our synthetic division is equal to the value of f of 11. So our remainder that we had, 12, equals what we get when we plug in 11. So I already explained remainder theorem a little bit in our previous example. We said, hey, well, if I divide x minus whatever value I want to evaluate this function at, I get a rewritten version that makes it easier to evaluate. So here I want to use this to find f of k. So what I really want is f of negative 1/2. So I could plug negative 1/2 in here and then like cube it, multiply it by 6 and all that. But I'm going to use my synthetic division to do this instead. So first off, I'm going to divide my original polynomial by x minus my value of k, so by x minus negative 1/2. So using synthetic division, my negative 1/2 goes on the outside there, and then I'll drop down 6, multiply it by negative 1/2 is negative 3, add those is negative 34, times negative 1/2 is 17, add those together, you get 2, multiply by negative 1/2 is negative 1, add and you get negative 1. I can use that result to rewrite f of x, my original polynomial, as x minus negative 1/2 times what I got when I did my division. So that string of numbers stood for 6x squared minus 34x plus 2 as my whole number result, and then minus 1 for my remainder. So f of negative 1/2, plugging it in there, when you plug it into your first binomial, you get 0 times whatever you get when you plug it into the second one. Don't really care. 0 times that's still 0. And then minus 1 is negative 1, which is equal to my remainder, and it always will be. That's why it's called the remainder theorem. This time I want to evaluate f of 2 plus I. So I could plug 2 plus I in for all those x's and simplify. but I'm going to use my synthetic division and remainder theorem instead. So that says go ahead and divide by x minus my value of k. So I'm dividing by kind of a weird looking expression here, but I'll put my coefficients down. My value that makes that equal to 0 is 2 plus I, my value of k. Drop down 1, multiply 1 times 2 plus I, you still get 2 plus I. Add those together, it's negative 3 plus I. Now when it comes to multiplying negative 3 plus I and 2 plus I together, that's going to take a little bit more work, so I'm going to jot it down out to the side here. And I will come up with negative 6 plus 2I minus 3I plus I squared. And then combining some things, I'll have negative 6 minus I squared is negative 1, which, if you put that together, gives you negative 7 minus I. Add that to 1, and you end up with negative 6 minus I. I'm not going to rewrite this in the different form like I did up above, because it would be quite messy. So f of 2 plus I, we know, is equal to our remainder of negative 6 minus I. So the whole idea of a 0 we've talked about before, but if you plug a value into your expression and you get 0 out, that means that number is a 0. That's why it's called a 0. And it means that that x value is the x-intercept on your graph if you were to graph it. So say you plugged in 2 to a function, you got 0 out, 2, 0 would be the x-intercept. We're going to use some synthetic division to decide if this value is a 0 of our polynomial. So I'm going to divide my original expression by x minus 2 and see if it divides in evenly, essentially, so that I get no remainder. So if I do this division, I get 1, multiply, add those together, get 4, multiply back, you end up with 0. So I could rewrite my original polynomial in the form x minus 2 times x plus 4 plus 0, which means if I was to plug in 2, I'd have 2 minus 2 is 0, times 6, I'd end up with 0. That also can be noticed by seeing, well, I got a remainder of 0, it divided in evenly. So f of 2 is 0, and 2 is a 0 of that polynomial.